Okay, yeah, we'll start. Okay, so we're going to talk here about a manufacturing challenge that we had. So yeah, this is taking place over in Huddersfield, so we've probably got the longest title here. So I want to give a talk and tell you a bit about the problem and a bit about how we solved it and things like that. Just before I start, I think it's, the talk doesn't really focus on the commercial aspects, because although this is currently undergoing trials with a company who have a lot of machine tools throughout Asia, we can't talk commercially about the integration. We can only talk about the application of planning. So some of the things are a bit loose, but I'll explain later. Okay, so just for those who don't know what a machine tool is, so a machine tool is a manufacturing device, really, a subtractive manufacturing device. So companies like Apple, they're aluminium bodies. They often start as a solid piece of metal and then they're subtractively machined out. There's a whole variety of configurations of machines for different tasks, right? There's very sort of small, compact ones for making dental implants and prosthetics and things like that, and then there's huge ones for machining aircraft wings and things like that. So there's a significant amount of them. So there's a real demand for increasing the accuracy of machines, right? And this is one thing that our engineering department in Huddersfield are particularly focused on and quite renowned for, really, improving the accuracy of machine tools for big CNC ones. So you can see that one there. This isn't one of our photos, but you can see it's a huge working volume, producing a part of a jet engine there. Okay, so we've done some work before on the use of planning for identifying motion errors and for measuring machines and calibrating them, things like this. But I just thought we'd just recap on why we're looking at machines and what we mean. Okay, so obviously these machines are huge structures, right? They're significant weight and they're moving around. The commanded position you move to is not where it's expected to go, right? There's a deviation there, and that's the error, right? Now, a significant amount of this error is made from the dynamic errors, things like the weight of the machine, the movement errors and things like that. But as long as it's systematic and repeatable, they can be removed by real-time compensation and things like that. But the thermal errors are much more troublesome, okay? Because sometimes, they are systematic and repeatable, but they don't behave in the same way. So I kind of just put this picture in here just to kind of explain what I mean there. So we've got kind of like a side snapshot there of a 3-axis machine tool. And you can see that there's some heat generated. I don't know if this works. Oh, okay. So there's some heat generated where it's red there. That's the spindle motor, which turns the cutting drill, if you like. That energy, when it's released into the structure, causes it to deviate, right? Now, because it's not a symmetric structure, no, it's symmetric side to side, but not front to back, it causes it to tilt. So it's quite troublesome, really, because you don't exactly know how much it's going to move, depending on the temperature. Okay, so now so I've talked a little bit about the error there and a bit about where these thermal errors come from, but let me just talk a little bit about why we're looking at energy and consumption there together. Okay, so if you just remember that slide I looked at back there where we've got the energy, or we've got the spindle motor turning around and the heat generated from that. Obviously, that's taking a lot of energy to generate the cutting forces. Now, as manufacturers are kind of moving to this sort of improving machines, so they're down to the micron accuracy, they're kind of covering all bases, and one thing they're looking at now is, well, energy is obviously being consumed, generating heat, and that's causing deviation. So they're now looking at reducing the energy consumption to improve the accuracy as well. So there's some figures here just to kind of quantify it in a loose way. Some studies have shown that 63% of the cost of energy manufacturing is through the machine tool. And for a not small to medium sized manufacturer with 15 machine tools, this can be about £10,000 per annum. So yeah, obviously the bigger the machine tool, the kind of more energy it takes. Manufacturers are obviously chasing this micron accuracy, and hence the direction of this research, really. So just to put kind of a graph there, just to show you what I mean. So here we've got 3 temperatures. So if you just remember that slide I had back a minute ago where we had the snapshot and the heat generated on the spindle, the 3 sort of thin lines are temperatures recorded at different locations there, and then the block is the spindle motor, so the actual turning of the cutting. So you can see that when there's a significant block of energy released into that, the heat generated, you kind of get the rapid rise of the temperature recorded, and then once it stops, it kind of reduces down. So just to show you that there is kind of a relationship between energy and temperature, which is kind of obvious, really, but this just kind of backs that up. So it's not just about energy consumption, though, because the temperature just changed with the external environment, right? So just to show you there, before this spindle is actually used, you can see the temperature's rising, and that's just due to the time in the day. So, you know, like, I don't know, the factory might start at 8 a.m. and as the temperature rises within the building, that causes the external heat to influence and also warm up the machine. So that's just, what this slide here is showing that as temperature changes, so does the error, right? So back to that slide again where it showed the deviation moving forward. That's what this is showing. As temperature changes, you get the angular change there. Okay. And this one here just shows that as the machine is doing nothing, there's still thermal change, okay? So I've got plenty of these graphs to show you thermal change. But anyway, let me just move to the actual presentation then and what the problem is, okay? So here we're going to talk about intervals, right? So what an interval is it's a gap between a manufacturing operation. So these machines, I don't know if they're manufacturing things like the laptop case, obviously they're going to manufacture one, move it off, and another one's going to come in, right? Now, if this is an automated assembly line or manufacturing line, it could be very quick, right? There could be seconds between the change here. But in some more traditional manufacturing environments where it's perhaps more operator-based, there's quite a significant gap there. So I mean, this could be a 15-minute period, it could be up to a few hours or something like that, depending on what they need to do. They might need to retool the machine, change the configuration, etc. So that's the interval. Now, obviously, because the temperature is changing throughout the interval, it's going to change the error, all right? So what we're looking at here then is we're looking at the potential to change the use of the electronic components within the machine to generate heat, right? To stabilize the accuracy of the machine in that interval. But there's obviously a trade-off there between how much energy you want to release into the machine structure through use versus accuracy, right? So just to differentiate this between some of the other research that is released out of Huddersfield, if you like, in a more engineering and control perspective, because they have kind of real-time systems where they're monitoring the temperature and they basically move the machine to a different position. This is great for new machines, right? And that's what the market's like. But the problem is that there's a significant amount of machine tools out there that don't have this kind of online capability, and they're really operator-based, okay? So it's completely up to the operator what to do within that interval, right? You know, they know that they need to achieve a high accuracy on their machine. They know they can do it by changing the configuration and the use of the electronic components, but they might not have enough time to work it out. So that's where this research comes in, okay? So when I talk about the electrical subsystems there, we're on about like the motors that move the machine around. It could be motors, it could be measuring devices, it could be actually the computational side of the machine as well, because anything that uses energy in there and generates heat is released into the structure. So why did we consider using automated planning for this? Well, obviously there's kind of a deliberation process going on here where the expert would kind of sense the machine, you know, look at the temperature, look at what they're doing, look at what they need to do next, you know, look what the manufacturing requirements are, and then decide what is best to do, what's the best operation of the machine during that period. So there's kind of a lot of things to consider there, and there's obviously a limited time available for them to do this. Now, sort of skilled experts are very good at this, right? People who become kind of familiar with the machine. So the company that we were doing work with for this project, some of their operators who have kind of worked with the same machine for like maybe 15, 20 years, they kind of know it inside out. They know exactly what to do with it. But the problem is, especially in the UK, and I don't know what it's like in the US, but these kind of skilled experts they're quite old now in their careers, if you like, and they're coming to the sort of retirement age, and the government has not really invested in the manufacturing sector, you know, kind of apprenticeship schemes and stuff kind of dropped off. So there's kind of a huge gap of unskilled experts coming in, and that's the issue, you know, getting them to use or have tools for the knowledge. So that's where this work comes in. Okay, so just a little bit then about the modelling. So I've omitted quite a bit of detail here, just kind of focused on some of the sort of what I think are the interesting points, just to show you what's going on. So we did originally model this in PDDL, and the deployed solution actually that we've got still does use PDDL as well. So what we kind of do is we model the relationship between the machine's axes, right? So the propagation order. So on the right there, we've got like a 3-axis machine. So we've got the X, the Y-axis, and the Z on the top. So we model that stack in order just by having some predicates really. We model the axis position. The reason we're modeling that is because obviously if we're going to say that we want to move the axis, we need to know what's its upper and lower bounds, if you like, and where it is on that. So we use some numeric fluence for that. And then we have a relationship between axes and components, right? So you have these axes of movement, and then you also have some components that drive them or are related in some way to them. And then we model energy consumption. So this information is kind of delivered to us by either the machine provider or by doing some analysis of the machine, so whether it's thermal, finite element analysis or something like that. And then we can kind of put it into our model afterwards. So we have a very simple way of actually modeling energy consumption. We kind of just, we broke it down into a few levels. So we have kind of off, idle, normal, medium and high. Now, you could, obviously, a lot of motors and things like that are linear functions, right? So yeah, okay, there's other approaches to this, but during some of the experimental analysis we found that in reality we could get good enough results by just going for these 5 levels of operation. We didn't need to consider the whole fine granularity, if you like. So we have actions that relate to each level of utilization, and these kind of model where the axis is moving up and down, or where it is, and what the components relationship is to that axis, and where the energy is released, and we kind of increase some fluence based on these to model it. Now, I've omitted a lot of things in that action, but I just put it there as an example. We do have the full domain and problem instances used to generate the results, which are on this website, which is also in the paper as well, so you can see them if you want. Okay. So then we have a few metrics that we use to actually record this. So we record the total error. Now the error is the modelled error or deviation of the machine, if you like, and then we also have the total energy used. This gave us the potential to kind of try a few different things where we could minimise the energy use, minimise the accuracy or the error, whatever you call it, and kind of like a standard deviation of them both. So what we also do is we have some timed initial literals which give us the bounds of the actual interval. So we can say, yeah, okay, we know we've got a 30-minute period where the machine's going to be inactive, and that's where we want to plan for. So we can kind of give the planner the challenge of selecting the actions between that. So all the information is coming in from doing some analysis of the machine. So we've kind of got a table here which is in the paper where we have all the energy consumption and the relationship to accuracy for each component and the axes. So just to kind of, this is pretty much all we could put in really regarding the way the system works, but just to kind of give you a mental image there. So we have a machine on the right there. The position and the temperature information is automatically extracted out of that onto a PC running close by. That's where we convert it into the problem instance, do the planning. We convert that into G-code, which is just the machine code, if you like. That's how to instruct the machine tool to use. We put that back on the machine, and it's up to the operator to press OK and start. The operator can modify it if they want. This is kind of where the approach actually kind of fits quite nicely, because the operator likes it because they see the G-code, what they're familiar with, so the integration kind of works quite well. So it's currently going under trial actually with one of our industrial partners, which provides machine tools for manufacture out in Asia. Quite interesting, and things seem to be going so far. It's been trialing for quite some time now. So just some quick results there, so we're out of time. What we did is, for the paper, is we had 2 machine configurations, a 3-axis, a 5-axis, and we considered some different durations, 30 minutes, 60 minutes, 120 minutes. And what you can see on the right there is the standard, so that's just the machine operator doing what they normally do, which is in some instances is nothing. And then the 3 different metrics on the side there, energy, error energy and the standard deviation. So just a quick graph there to show you, which is kind of what you'd expect. If you minimise energy, obviously the error increases, you minimise error, the energy increases, and then there's kind of a compromise in the middle, which is really what we want. Okay, so just a quick summary there. So in terms of manufacturing and the engineering domain, little interest has actually been spent in this area, but as the engineering manufacturing community are kind of driven to saving energy, improving accuracy, niche sort of challenges like this are coming out. So it's quite interesting, and we seem to have produced quite a nice solution with automated planning, which seems to work quite well, and it's currently undergoing industrial testing. Okay, thank you.
Are you using G-code to handle all sort of nasty, complex optimization and constraint reasoning?
So G-code for the machine is actually very simple. It's just kind of move this axis from this position to this position at a certain speed. The actual machine itself does all that behind the scenes. So the machine has like a standard controller where they parse the G-code information and do all the geometric reasoning. We're kind of on a higher level, if you like.
So you're not doing a sort of detailed
no.
sophisticated modeling of...
No, that's all done for us. That's already there.
Pardon?
That's already done for us and handled in the background, if you like. We're away from that.
You know, when I was listening to your presentation, it may seem that this machine tool is rather specific. Would you disagree?
Yeah. So well, the one for this work is, yeah. So,
but how can you generalize?
oh no, it is. The model is generalized. So machines often differ in terms of like the number of axes and the length. So you can change the model, no problem for that. Yeah. But the work we did is for a specific one. Yeah.
So, like other domains where this could come to discussion, have you guys thinking about those?
Well, like other applications for this, yeah, I'm not so sure to be honest. No, but maybe there are some areas of overlap. Yeah. Okay.
Any other questions? Any other questions or comments? So then, thanks to the
Thank you.
speaker.